So let's start. My name is Vladimir Ivanov. Good morning, everybody. And today I want to tell you about mesh encode snippets in Java, the experiments we have been conducting for the past year. I started in last September, right after JVM Language Summit. So, a slide from the sponsor. And another notice from me, it's a work in progress. Nothing is finalized, nothing is finally decided. So I would like to tell you about the experiment, the results, and how we ended up there, where we are right now. So on a JVMLS page, there is a notice. We will speak bytecode here in this room. Unfortunately, there will be no bytecode in my presentation, only mesh encode, assembly code for x86. So let's start. So first of all, I will give some background to get you up with the problems we are facing and the solutions or interim solutions we came up with to solve the problem. It's a mesh encode snippets to simplify our prototyping work, and the vectors. We tried to bring up vectors on Java to Java platform to assist vector API implementations. So probably some of you have used that site. It's an intrinsic guide by Intel guys. So there are lots of intrinsics in C++ compilers in order to expose different vector instructions. So till recent times, it was there were around hundreds of instructions, and with AVX 512, lots more intrinsics are coming. So instead of hundreds, we have thousands of intrinsics. So we started to looking into that, and John pretty accurately summarized our feelings at that moment. So it was quite hard to reason about AVX, to try to play with it, lots of instructions, many differences between different vector extensions. We have AVX, we have AVX2, we have SSE4, different variants of SSE. So we wanted to bring up a sane model of vector programming to Java, and we started Vector API project. Jan will tell you about Vector API in much more detail, and I will focus on a question how to expose all those instructions to Java, because we want to implement as much of the implementation, to have it as much as we can in Java, and we have to access all those instructions. So till now, we have two ways to solve the problem: use JVM Intrinsics or switch to native code. So what is JVM Intrinsic? JVM Intrinsic is some hard-coded implementation in JVM for well-known methods. So it's either handwritten assembly or expressed in compiler IR. And for example, many methods in class are intrinsifiable by JIT compilers. For example, class.isInstance is an intrinsic. In Java 9, we introduced a new annotation called hotspot intrinsic candidate to make working with intrinsics, maintaining them much more manageable. So if you browse the JDK code and you see this intrinsics in such annotation, it means that VM knows about that method and tries to optimize it. The other solution is GNI. It's there from the very beginning. And if we want to expose the intrinsics through a GNI, we can come up with a bunch of GNI methods. Like we have a native method in Java, some helper class, and have a native implementation, which actually essentially has the intrinsic we need. why is it not that good idea? Because we have thousands of intrinsic, and we have to create a method entry point for every method. Also, invocation of overhead is also prohibitive for our purposes. Last year, I gave a demo on JVM language timing, show you the native method handle prototype in Project Panama. We did. So we have method handles in Java since Java 7. They work really good for Java methods, but they don't know anything about native methods. Why don't extend them to that? And here's a simple example how it works. So like construct a method type, look up a native entry point, and invoke it. That's it. It fitted pretty well the implementation we have, Java long invoke implementation we have in GDK. So almost all the pieces have a counterparts for native methods. And from the user perspective, the invocation of native method doesn't differ from invocation of Java method. And with the proper support on compiler side, native method handle call can be turned into direct call in the generated code. And it saves us some time during invocation, which is pretty good for such small code we are interested in. What are the benefits and pros and cons of these approaches? So native methods allows you to expose arbitrary native code, but it involves some ceremony. For JNI, it's much better for method handles, but still invocation overhead is non-negligible, it's non-zero, and still the actual code is a pack to the JVM and the optimizer. On the other hand, JVM Intrinsics provides you with the full power of the JVM. You can do whatever you want, but it's quite hard in terms of development and maintenance. You should hard code and teach VM to speak all those intrinsics, and we have many intrinsics we are interested in, many instructions. So, well, we want to avoid that. So we came up with an idea of machine code snippets. So let's come up with a new breed of method handles, which actually, let's cross native method handles and intrinsics and come up with a breed which doesn't suffer from all those problems. So the idea, the first iteration, is let's wrap a raw machine code in a method handle and expose it to the user as a method handle. So what are the primarily use cases? First of all, prototyping. We want to minimize implementation code, allow to define new method handle as simply as possible, give a decent performance comparable to JVM Intrinsics, and we are interested in pretty small snippets in size, up to dozens of instructions. For vector API, we're interested in almost single instruction snippets. So existing solution don't match either first or second point. So let's start with an example. Consider we want to vectorize a move operation. We have a system array copy, and we want to move data from one array to another. In Java, we can do that element by element. It's pretty inefficient. We have better ways these days. Let's try to vectorize it. We have a fancy 256-bit registers on x86 CPUs these days. Let's try to use them. So we read 256 value from memory and write it right away. So with a snippet, it looks that way. So we have a method handle. It has a method type, and it wraps a machine code, raw machine code. So the first question is, what are the registers? What do we address? in the snippet. We have some Java values, Java data source. Source is an object, offset is a raw offset in this object where to start reading the value, and dest is a base pointer for the result, and offset 2 is the offset is the destination object. So what are how can we pass the parameters into the code between Java code and native code? So we have to come up with some implicit assumptions. And let's use platform ABI for that. So we have a method handle with a method type. It has a number of arguments, and we assume every argument has some predefined location. So we have RDI, RSI, RDX, RCX. Fine. So great, we have a method handle. We have machine code wrapped in a method handle. So is it enough? Not really. We have different execution modes in the JVM. So we have optimized code produced by JIT compilers, and we have interpreter. And we want method code snippets to work in both modes. So to get it sane, we need 2 different versions. I call them standalone. A standalone version of machine code snippet akin to native method, which can be invoked from all execution modes. And for optimized code, JIT compilers knows how to embed the snippets into the generated code. Embed, I mean gluing in the right into the generated code. Calling conventions matches native ABI for simplicity. So for simplicity, that's a simplifying assumption. So let's try to match native ABI to make our life easier. So we have on Linux x64, we have 6 registers for integral parameters. Let's use that. Also, to expose machine code snippet to the JIT compiler, I introduced a new entry point, machine code snippet, which extends native entry point. And this entry point holds the actual machine code snippets code the JIT compiler can grab it hands-on. And native entry point holds the address you see, right? So there is an address field. It's a raw address of the entry point. So when JIT compiler issues a direct call for the native method handle entry point in the generated call, it reads that field. It can do the same for the machine code snippet and extracts raw machine code from there. How do we define machine code snippets? First, so the API looks like that right now. It's a first stub. It's not finalized in any way. It's just the first version I come up with, and it solved the problem. I haven't invested any time in polishing it yet. So there are 2 important pieces there: method type of the method handle, which will be produced, and the actual method code. So for our snippet, it looks like the following. We have a name. Let's copy 256-bit. The type is return type void. To a register addressing mode, base pointer plus offset, and the destination base pointer plus offset. Requires AVX. The instructions are available only on AVX. As part of AVX extension, and the machine code encodes 2 machine instructions we are interested in. So the standalone version looks like the following. So some ceremony before and after, like setting up the frame, and the machine code we are interested in is simply embedded. And the arguments are passed in the registers we implicitly agreed on, so matching native calling conventions. It's pretty unwieldy to use method handles directly. So every invoker throws an exception, throwable exception, so you have to handle it. So it's convenient to wrap the method handles in some kind of method to simplify, to use it in a more uniform fashion. So here is an example of unsafe wrapper for the method handle we came up with. And let's see how does JIT compiler behave. So we see the following inlining: invoker, check type of the method handle, and then invoke native. So extract entry point object, and I'll invoke it, and when JIT compiler sees the entry point as a compile time constant, it extracts all necessary information from it. And the machine code looks like the following. So we have almost the same version as we have with the standalone version, and it's optimized. So it's produced by JIT compiler, so it embedded the machine code in the produced code, the same code we asked for. But we have some register-to-register moves, and the reason is why. And the reason we have that because calling conventions in JVM for Java code and native calling conventions slightly different. How many of you heard about Java calling conventions before? Wow, quite many. I'm surprised a little bit. But in Java, it's not specified. It's an area of VM implementation. So VM implementation is free to choose whatever calling convention it is interested in. And for speeding up GNI calls, Hotspot has a special calling convention which shifts the registers one step. So when you call a native method, you can put GNI env pointer in the first register, first parameter register, without shuffling other registers. And it works pretty fine. That's why we have all those rec-to-rec moves in the code. And for standalone version, the same task is solved by linker method. So when we call from Java code to standalone version, we go through a linker method, link to native, and it does shuffling, argument shuffling for us. So like doing that shift. And to expose that functionality to user, we have to provide some safe wrapper. So here is an example of a safe wrapper. We do array bounds checks, compute offsets, and then call unsafe wrapper. That's how it's intended to use. So 3 levels. The lowest level method handle, which wraps machine code, then unsafe wrapper, and then safe wrapper, which can be exposed as a part of, for example, public API, if you're interested in. So let's switch to a more interesting example, and let's look at the packed operations. VP add packet integers. It's supported starting AVX2, and it sums to 256 vector registers and puts the result in the third. So how could we expose such instruction on Java level? We have to express vectors, 256-bit value. Well, do we have anything right now? Well, not really. We have to come up with something new. John and Brian, a couple of years ago, came up with a new term, impedance mismatch, when they talked about JVM and language evolution. We have a similar problem on hardware, with hardware as well. Hardware evolves, new instructions are added, new registers, larger registers, are exposed to the on the mesh encode level, but the JVM type system stays almost the same. So if we want to expose the values larger than 64 bits, we have to refrain to some tricks. So for the prototyping purposes, we came up with 3 new classes, long2, long4, long8, to represent 128 and larger bit values. They are value-based classes. Right now, until we got value classes, they are intended to be value classes and treated in the following manner. They are well known to the JVM. JIT compilers have to treat them specially to be able to match them to vector registers, and I have implemented support in C2 to do that. I'll talk about that later. So until value types are there, we can't consider them as the first-class citizens. But once we have value types, we hope we can be able to make them as optimizable as primitives. So, okay, so we have long4 right now to describe UMM register. So what's next? We have a new signature, 2 arguments, long4, but our current calling conventions don't allow us to call that code right away. So we have to somehow put the value from the box to vector register. So VM should provide implicit boxing and unboxing operations between these newly introduced boxed to get the layout the mesh encode expects. So here we have 2 unboxing operations and the boxing operation after the result is computed. And what to do with the result? It's an object, and we have a mesh encode. We should somehow allocate that box. So we should provide a pre-allocated box for the result in that particular case, and it's placed in the first, it's prepended to the arguments and passed as a first argument. So here we have, we box the result into pre-allocated box. But we don't need to ask users to do that. We can do that underneath. For example, either explicitly pre-allocating box and passing it into the method handle in an unsafe wrapper, or, well, construct an appropriate method handle, which does exactly the same job. So for the user, it's exposed as the method handle with the same method type as was requested, but when it's actually invoked and before calling mesh encode, the box for the result is allocated. So here is a standalone version, and it contains all necessary boxing and unboxing operations. We need to provide the correctness. In the blue, there is the mesh encode we asked for. And in a JIT compiled code, we have the same operations. So we get boxed values, we extract values, we execute the snippet code, and then we box the result and return it. Because Java code doesn't expect the values such large. So in order to be able to work with it from Java code, we have to expose them as a box, in a boxed form, like as a long2, long4, long8. Let's look at a more complicated example, nested operations. So here is the JIT produced code. Snippets are in blue, boxing and unboxing operations are in green, and the instructions we don't want to see in the code are in red. So that's some artifacts of JIT compilation we want to get rid of. So what's the problem here? We have we have many snippets in the same compilation unit, in the same code, but they have exactly the same shape. So they use the same registers, so they conflict for the same registers. So JIT compiler has to move the values, live values around, spill them, and fill in order to preserve them across snippets, because they actually destroy that values. How can we fix that? Well, with the current assumption, we can do that, but let's change that. Let's user help us with that. So let user know about register allocator decision, what compiler does. So let's switch from raw machine code to so-called snippet recipes. So ask user for a recipe of the snippet he wants to use instead of raw machine code. So in compiler, we are interested in register masks. What registers can we use for arguments? With the calling conventions, but native, we have a fixed registers. We want to relax that constraint. So how to describe that register masks? Fortunately, in Java 9, we have JVM CI interface coming. And among other things, it has register definitions in platform configuration files. So we can use that. Let's try. So here is a refined API. So instead of asking for a raw machine code as a byte array, let's ask a user for register masks for the arguments, and the snippet generator, which is an interface which gets in, it's a functional interface which for a number of registers, so register allocator chooses the registers from register masks, feeds them into the snippet generator, and gets the specialized machine code back. So it allows to specialize the snippet for the actual use sites in the generated code. So the code should be much better. Generated code should be much better. So here is an actual example. So we have method types as we have before. So long, 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 two long for arguments, and the long for result. Here are the register masks. Any XMM register can be used. And here is a snippet recipe. We get a register for every argument for return type, and we have in this generator, we have to produce the machine code which complies with that constraints. So, okay, let's encode the registers we have got from the compiler and produce the instruction. It looks more complicated, but the main problem is that we don't have assemblers in Java. So that's with the proper API, it should be much simpler, and Graal has a macro assembler, so it should be used to produce raw machine code from Java, and the API will look much, much better. The code will look much, much better. Okay, here is a code with for register allocator AVS snippet, and we see we don't have any spills here, and the following snippet has a different registers used than others. So, and no register-to-register moves or spills here. But still, there are some instructions left. So what can we do with that? And the thing we haven't thought about before is effects. So when we we agreed to obey the calling conventions. So calling conventions fix the argument locations, but also preserved registers are also defined by the calling conventions. So implicitly, there is a number of registers which are killed across a call, which aren't preserved across the call. And it causes the JIT compiler to conservatively move the values out of the registers to avoid their destruction. So on Linux x64, all XMM registers are destroyed across calls. So that's why we see unnecessary spills. Let's fix that. Let's make the preserved register set explicit. Let's say this particular snippet doesn't kill any registers. And what do we get? Well, much smaller and much cleaner code. No more, well, there are at least 3 unnecessary instructions, but 2 of them, spill and fill, the second and third, are caused by an allocation we have. So allocation involves a call, native call into JVM runtime and a slow path, because if we ran out of memory, we have to try to free some. And it's a call into a native, another method, so another function, so we have to obey the calling convention there. So UMM is spilled because of that. And there is one reg-to-reg move upper, which is also attributed to that particular allocation call, because we use RBP down. We use it here. See? So here is it. So that's all about machine code snippets. Let's look in more details on vectors and box eliminations. So as I told you before, for every vector snippet which returns a vector value, we allocate a box. That's kind of scary if we can't rely on box elimination, box unboxing elimination, because, well, why do we care about code quality if we box and unbox around snippets? Well, so how does long2 look like on how it's declared? So until we have value types, we have to do some precaution ourselves, some boilerplate things ourselves, like we want to use factory instead of construction, so boxes are forbidden to explicitly allocate it. Only factory should be used. Everything is intrinsified for that purpose. And there is still one thing which is marked as fix me. Field declarations, L1, L2. What's the problem with that? So here is a heap layout of the long2 box. So we have a header, and we have a payload, 2 longs, 16 bytes. And we want to operate with them in as a single location, like with a single instruction. Load 124 bits and put them back. We don't want to mess up with all the halves. What's the problem with the halves? Well, if we want to, we can hard code that on a Java side, because depending on the platform, we have big Indian and little Indian architectures. So how do we know what half correspond to what part in value? Well, we can't do that. So what we would really like to do is to have a box with some payload of desired size. So some kind of intrinsify the knowledge of the box in the JVM and enable the values larger than 64-bit on JVM level, not on the JVM type system, but at least on JVM level. Another thing is, if you noticed, I think some of you noticed that all the spills are unaligned loads and stores. And we do the same both in generated code and boxing, unboxing. We do explicitly in the code for loading and storing the result of vector operations. And JIT compiler does the same. Why it's so? Can we use a faster aligned variant? Well, not now. The heap alignment is 8-byte boundary. That's what garbage collectors guarantee us. And we can guarantee that the vector value is naturally aligned. And for a vector value, natural alignment is its size. So for long 2, we need 16-byte alignment. For long 4, we need 32-byte alignment. And long 8, we need 64-byte alignment. And without garbage collector assistance, we can't do that. So we have to stick with with unaligned loads and stores. We can fix that in generated code because we are in full control of our stack layout, and we can align it at the beginning of the generated method. So regarding boxing, right now in the current prototype, C2 treats specially the boxing operations on vector values. So there is a special node called vbox, which is produced for the snippets result, and it conditionally puts the value produced by a snippet into pre-allocated box. But if the call snippets are nested, it goes away. So the result is used as is, without any boxing and unboxing. So we have boxing only at the beginning when we load something from heap, then operating mostly in registers or spills and fills, and then box the final result into the heap. Another thing which is interesting in the generated code is the value, the spills and fills across a call to a new instant Java. It involves a save point, because if there is no memory left, we have to save point and run garbage collector. But you see, we can de-optimize at that point, but we don't box and unbox it. We have a raw value. How is it correct? If we de-optimize at that point, will we still be running? Will JVM crash or what? So JIT compilers preserve the correctness. For that particular point, there is a meta information attached which instructs the de-optimization logic to box the result from on top of stack. As you can see, here is stack 0 slowed, stack 0, and it corresponds to the actual location of that value. So during the optimization, JVM will automatically box the results, and we are fine. But in generated code, we have very efficient representation. So JVM is pretty smart about treating vector values right now. What can be improved? Well, why can't we move allocations around the code? So we have 3 instructions here, which are necessary which are added by that call new instant Java. If we move with upper, there is no need in those instructions. So, but C2 can do that because every allocation is a possible save point, and save point has a state, JVM state attached, so we can't freely move the allocations. But with the value types and hazing boxes, they bring us, it should be solved. So I'm really eager to see a hazing box prototype and try it out. There is another effect, repeated boxing. It's some JIT compiler artifact. I don't know. Frankly speaking, I haven't invested. I haven't explored yet why it happens. Instead of spilling on heap or on the stack, the value is spilled on the heap. Let's call it that way. So we load the value from the heap twice. It's not that bad, but still it's possibly less efficient than having the value spilled on stack. So let's look at the more complex example. Let's try to vectorize naive hash implementation. Here is the function. Let's try to vectorize it. So let's let's try to vectorize hashing a byte array. So we read values by 8 bytes, expand that to integer values, and then process them. And do that until we ran out of content. And then sum the final result up. So it looks in Java code, it looks like that. Here we have a loop body, vhash8, and we read a long value from the byte buffer, byte array, and pass it into the processing function vhash8. So how does the code look like? So here is a C2IR, and you can see, so in gray there are snippets nodes, green are boxing unboxing operations, and we can see that all the snippets operate on vectors, raw values, no boxing unboxing involved, but we have boxing and unboxing when we start executing an iteration, and we leave it when we switch to the next iteration, and well, we are in a loop, and it's pretty bad, right? On every loop iteration, we do boxing and unboxing. What went wrong? So here is the problematic store vector we haven't eliminated. That's the result of the loop iteration. It stores the result into ec local, but it can't eliminate the box. Why? The problem is limitations of escape analysis in C2. So initially we have the first value of the accumulator, it's 0, and then we update it on every iteration. And on IR level, we have a phi node for that value, and C2 can't eliminate that case. It doesn't, the current implementation doesn't cover it. So it causes also the other loads. So we have an allocation in the loop body. So we have to spill values around. And here we have a bunch of constants used. So in the algorithm, we have a number of pre-computed vectors, which are used for multiplication to get the necessary result. And here we see that those loads are coming from constants. So we load a constant value, put it in a register, use it, and then destroy it. And then on the next iteration, we load it again. So that's another inefficiency in the generated code. So it's not that bad, considering we have to spill around the allocation, box allocation for that, for the result of the iteration. But anyway, I haven't fixed the following bug. So probably if the problematic boxing goes away, the other unboxing operations will go away as well. So here's a bunch of observations about escape analysis in C2. So the problem with phi nodes, vectors aren't hoisted out of the loop, those constants. repeated unboxing, and the box allocation placement. So that's almost it. The current status of the prototype is it's almost feature complete. I focused on C2 support on Linux, Solaris, and Mac x64. The prototype has been used for a while by Jan Graves for experiments with Vector API. And thanks to Paul and Jan for the feedback and for the bug reports. That was really helpful. And without your help, it wouldn't be that. So what's the remaining work? So there are some missing features left. So it would be nice to have temporary registers in the snippets. Also, some instructions require an alignment. And right now, there is no way for a snippet to know where it will be placed. But I showed you register allocator aware snippets. It can be extended to location aware snippets as well. The compiler knows where it will embed the snippet, and it can pass that information into the snippet recipe, the snippet generator. And improve error diagnostics. So more errors are helpful, more diagnostic errors are helpful when you inject inherently unsafe code into the JVM. So if it causes a crash, it's better to see it right away and not try to diagnose it. So probably it's a good time to start prototyping on other platforms, try to how it looks like on Spark and ARM64. Support is in other JIT compilers like Graal and C1 is also a good way to interesting experiment, because right now there is only C2 support, so probably some of the C2 assumptions can sneak into the API. API is a problem as well, so a better way to declare snippets is also necessary, and the escape analysis should be enhanced, not necessarily for arbitrary Java objects, but for vector boxes, so like prototyping Hazen boxes support, the boxes which don't have identity, don't preserve it. How much time do I have? Okay, a couple of more slides. So example, multiple return values. We have a CPU ID. What did I mean by why do we need multiple return values? So CPU ID returns two results, two values in two registers. And we have to box the result ourselves to pass it to the user. So long2 is a good candidate. It's exactly enough, barely enough space for 4 ins. And in generated code, it looks like the following. So if we want to extract one value, we have to put all the values into the box, so all 4 produced values into result values into the box, and then extract the value we are interested in. There is no boxing involved here because we construct in the register, but still we can't eliminate that packing the result into the register. So if we expose on an IR level that the snippet produces multiple values instead of one, we can say that, okay, there is, here is the result you're interested in, and JIT can use it right away without all that boxing. So that's it. Here are the links. Please, if you are interested in that, please try Project Panama. We have an extensive number of samples to work with. Thank you very much.